Okay, let's unpack this. Did you know that these incredibly advanced AI systems, vision language models, are now so sophisticated they're being used in robotics for really complex tasks like planning surgeries?
Yeah, it's pretty wild.
And not only that, but they're even getting good at understanding and like generating humor by creating memes in over 110 languages. Pretty mind-blowing, right?
What's fascinating here is the rapid progress. Vision language models, or VLMs, they mark a real breakthrough in AI. They're not limited to just processing text anymore.
Yeah.
They can now, understand the visual world through images and videos and combine that with their language abilities.
Exactly. And you shared this incredibly comprehensive survey, it's huge, titled Benchmark Evaluations, Applications, and Challenges of Large Vision Language Models, a survey. It covers pretty much everything from 2019 up to now 2024.
Right.
So our mission for this deep dive is to pull out the most important insights about VLMs for you, how they actually function, what they're capable of achieving, and the challenges that still lie ahead.
If we look at the big picture, VLMs are addressing a fundamental constraint of language-only models. While models that only process text have been, well, very successful, the real world, as you know, it's full of different kinds of information.
Sure.
VLMs bridge this gap, allowing AI to perceive and reason about the world in a much more holistic way.
That's the core idea, isn't it? You shared this fascinating survey, and we're going to break it down for you, highlighting the aha moments and keeping the technical details straightforward. We want you to finish this feeling well-informed and genuinely excited about the potential of VLMs.
Sounds good.
So let's start with the basics. What exactly are VLMs, and why should this be on your radar?
Essentially, VLMs are systems that bring together computer vision and natural language processing. Think of it as giving a language model the ability to see, to process and understand visual data like images and videos alongside text.
Okay.
This combination allows them to go beyond what models that only handle one type of information, one modality can do.
Okay, so they're not just reading words, they're also taking in pictures and videos. That makes sense. But what makes this such a significant advancement? What can VLMs do that previous AI couldn't?
Well, the truly transformative aspect is their ability to reason about and understand complex information that is both visual and textual. The survey highlights several powerful VLMs as examples, like CLIP, Claude, GPT-4V, Flamingo, Llama 3.2 Vision, and Gemini.
Right, the big names.
Exactly. These models have demonstrated impressive capabilities, even surpassing traditional computer vision models in tasks like zero-shot classification.
Zero shot. What does that mean exactly?
It means they can recognize objects and concepts they haven't been specifically trained on.
Wow, so they can just figure it out on the fly. That's really powerful. So it's not just recognizing a dog in a photo if they've seen countless dog pictures before.
Precisely. They develop a more general understanding that allows them to apply their knowledge to new situations. And this opens up a wide array of real-world uses, which the survey details quite well.
Okay, like what?
Consider visual question answering, where you can ask a VLM about an image, and it can provide detailed and relevant answers. Then you have autonomous driving, where understanding the visual environment is obviously critical.
Absolutely.
And embodied agents, which are AI systems that can interact with their surroundings either in virtual worlds or, the physical world.
Embodied agents, like robots that can understand what they're seeing and react accordingly.
Exactly. However, the survey also points out a unique challenge that arises from this combination of vision and language.
Yeah.
Visual hallucination.
Visual hallucination, what's that?
This is when VLMs produce responses that aren't actually based on what's in the visual input. They might describe things that aren't present or misinterpret the scene.
Visual hallucination. That sounds a bit like the AI is making things up based on what it anticipates should be there.
That's a good way to describe it. It's a key area of ongoing research to understand and reduce this issue. Now, let's dive into how these remarkable models are actually constructed. The survey outlines the main architectures and training methods that have evolved from 2019 to 2024.
Okay, so how do we get from just language models to these powerful systems that can understand both text and images? What was the big shift?
Well, the survey highlights a significant shift in the development process. Initially, researchers were training VLMs from the ground up, building everything from scratch.
Right.
However, the trend has shifted toward leveraging the capabilities of pre-trained large language models, LLMs, as a foundation. Think of it as building on a very strong base provided by an LLM and then adding the visual processing abilities on top.
That makes sense. It's likely more efficient than trying to build everything from scratch each time. The survey mentions three main research directions in how this integration happens, right? Vision-language correlation, architecture, and benchmarks. Let's start with correlation. What's important there?
So vision-language correlation focuses on how the training objectives and the overall design of the model help to bring visual and textual information together effectively. One key training objective mentioned is contrastive learning.
Okay, contrastive learning.
Right. You might be familiar with SimCLR, which was originally developed for visual tasks. The survey explains how this idea is adapted for VLMs by training the model to recognize when an image and a piece of text are related. This brings their internal representations, their embeddings, closer together in the model's embedding space while pushing apart the representations of unrelated image-text pairs.
So it's like teaching the model what belongs together and what doesn't. Like showing it a picture of a cat and the word cat and saying, these are a match.
Exactly.
Then showing it the cat picture and the word dog and saying, these didn't really go together.
That's a perfect analogy. Now, the second direction is vision-language architecture. What are the key trends in how these models are structured?
From what I understood, the earlier approaches involved training everything from scratch, like the initial versions of CLIP maybe. But the newer approaches heavily rely on those pre-trained LLMs like Llama 3.2 Vision to get a better grasp of understanding visual content.
That's right.
It's like giving the model a really intelligent language processing center and then teaching it how to interpret visual data.
Exactly. The architecture is crucial in determining how well the visual and textual information can interact. The survey breaks down some common architectural components. First, there's the vision encoder. What's its role?
That's the part that takes the image or video and converts it into a set of features embeddings that the language model can understand, right? The survey mentions examples like CLP, BLA, ResNet, and vision transformers, or VITs. It seems these are often pre-trained on massive image data sets like ImageNet.
That's correct. And that pre-training is really important. Pre-training the vision encoder on large visual data sets allows it to learn general visual features, which is much more effective than starting with a randomly initialized encoder. It's a form of transfer learning, leveraging existing visual knowledge.
Got it. Transfer learning.
Then what about the text encoder?
That sounds like the equivalent for text, taking words and converting them into those embeddings. The survey notes that older models like early CLA and BLA use these. However, it also mentions that more recent models like Elevate often skip this and directly use the LLM for text understanding.
That's a significant development. The trend is definitely to rely more on the powerful text understanding capabilities of the LLM backbone itself.
Okay.
Instead of a separate text encoder, these newer models use projection layers or cross-attention mechanisms to connect the visual input directly to the LLM.
And what about the text decoder? That seems pretty straightforward. It's the language model itself, acting as the text generator, guided by the visual features that the vision encoder has extracted. Models like GPT-4V and Flamingo use this approach, often with a fairly minimal way of feeding in the visual information.
Right. They capitalize on the LLM's strong language generation abilities.
Yeah.
Now, you also mentioned cross-attention mechanisms. What are those for?
These act like bridges, right, between the visual and textual features. They allow the model to identify which parts of the image are most relevant to the text, and vice versa. The survey mentions VisualBERT and Flamingo as using these, but not the early versions of CCOLIP, interestingly.
Precisely. Cross-attention enables a more dynamic interaction between the different types of data.
Yeah.
Now, let's talk about how these models are trained. The survey outlines two main approaches, training from scratch and using LLMs as a backbone. What are the key aspects of training from scratch?
That often involves self-supervised learning, or SSL, where the model learns from unlabeled data. The survey highlights techniques like masked image modeling. Contrastive learning, again, seems important, and predicting image transformations. It looks like contrastive learning is really central here, used by models like CLEAP, Belay, and Align to align those visual and text embeddings.
Exactly. By learning to determine which images and text belong together in that shared embedding space, the model develops a fundamental understanding of the relationships between the two modalities. Now, what about the methods used when leveraging LLMs as a backbone? That's the newer trend.
That seems to involve something called a projector. It maps the visual features to align with the LLM's text embeddings. These projectors are often multi-layer perceptrons, or MLPs.
Okay.
The survey mentions models like ELAV and Qwen2VL as using these, and this projector can be trained in different ways, either alongside the LLM or with the LLM's weights frozen, which sounds efficient.
That's right. Freezing parts of the LLM can be a way to maintain its pre-trained knowledge while focusing specifically on aligning the visual input. The survey also mentions joint training, where everything the LLM, the projector, the vision encoder is updated together, as in Flamingo.
Right.
And then there are freeze training stages, where you might freeze certain components, like the vision encoder, while fine-tuning others, like the projector, and maybe parts of the LLM.
It sounds like there are many different ways to combine these components and train them. The survey also touches on some newer architectures, right? Things like treating all modalities as tokens and something called transfusion. What's the idea behind those?
Yeah, these represent more recent innovations in how VLMs handle multimodal input. Treating all modalities as tokens is a really interesting approach. Models like EMU3 encode visual inputs, images, and videos as sequences of tokens, just like text.
Huh.
They even use spiral tokens to mark the beginning and end of visual information. This allows for a more unified way of representing and generating both visual and textual content as basically a token prediction task.
So instead of treating images and text as fundamentally different types of data, the model sees them all as just different kinds of tokens in a sequence. That's a pretty clever idea. And transfusion.
Transfusion involves processing different modalities, like discrete text tokens and continuous image vectors, simultaneously within a single transformer architecture. It's a bit more technically involved, with strategic points where the processing differs based on the modality, but it shows promise for creating even more integrated multimodal models that can handle diverse input types in a more unified way.
This is all incredibly complex, but the survey does a great job of explaining it. Now, once you have these VLMs built, how do you know if they're performing well? That's where benchmarks and evaluation come in, right?
Exactly.
The survey mentions a rapid increase in VLM benchmarks since 2022.
Absolutely. As VLMs have become more advanced, so has the need for thorough evaluation. These benchmarks go beyond simple visual question answering VQA to test a broader range of abilities, such as mathematical reasoning and understanding complex scenes. The survey categorizes 38 different benchmarks into 10 primary categories.
10 categories. That's a lot of different ways to test these models.
Yeah.
Figure 2A in the survey gives a breakdown, with visual reasoning being the largest category at around, 22.7%?
Yeah, about that.
That makes sense, given what we've been discussing. What are some other key categories?
Other significant categories include understanding multilingual, multimodal information, which is interesting, optical character recognition, or OCR.
Reading text and images.
Right. Understanding charts and graphs, generating images from text, evaluating for hallucinations, which we talk about general multimodal intelligence, understanding videos, and then specific areas for robotics like robot simulators and robotics benchmarks, even evaluating world models.
So a really diverse set of tests to see what these models are capable of. Now, how is the data for these benchmarks actually collected? It can't all be humans manually creating questions and answers for everything, can it? That sounds like a ton of work.
No, it's definitely a challenge. The survey outlines a few common data collection methods. Data sets that are fully annotated by humans are considered, the gold standard for quality. Humans create or find challenging test questions. MMMU is an example where university students from various fields collected existing exam questions.
Okay.
But as you can imagine, this is very time-consuming and difficult to scale up.
Yeah, getting enough human annotated data for all these different tasks must be a huge undertaking. So what are the alternatives?
Well, data sets that are partially human annotated but scaled up using synthetic data are becoming increasingly popular. In this approach, humans might provide initial examples and then powerful language models. LLMs, again, are used to generate more questions and answers. This is common for tasks like understanding charts and videos.
Right.
However, as we discussed earlier with hallucinations, LLMs aren't always perfect and can generate inaccurate or unfaithful content. So these methods often include automatic filters and validation by human workers to ensure quality.
So AI helps to create the test, and then humans double-check to make sure that AI didn't make any mistakes. That sounds like a practical approach. Are there other methods?
Yes, there are also partially human annotated data sets scaled with synthetic data that undergo full validation by humans, which is even better quality but more costly. And for robotics, there's evaluation through interaction in simulators.
Oh, the virtual worlds.
Exactly.
Yeah.
Here, VLM-powered agents are assessed in rule-based virtual environments. This helps to overcome the scarcity of real-world robot data, but can introduce what's called a sim-to-real gap.
The sim-to-real gap.
Meaning what works perfectly in a simulation might not translate directly to the complexities and unpredictability of the real world.
That makes sense. A virtual robot might behave differently than a physical one, facing unexpected friction or lighting changes, things like that. Now, when these VLMs answer questions in these benchmarks, how do we actually measure how well they're doing? What kind of metrics are used? The survey mentions mostly automatic metrics for scalability.
That's right. Automation is pretty much essential for running these evaluations on a large scale. The metrics used often influence how the questions themselves are formatted. Figure 3 in the survey shows that many common metrics focus on short-form answer matching.
Okay, like what?
This includes things like exact match, where the VLM's answer has to be exactly the same as the correct answer. Simple enough. However, the survey points out that exact match can miss answers that are essentially correct but phrased differently.
Right, so if the correct answer is the car is red and the VLM says a red car, it might be marked as incorrect even though it conveys the same information. That seems too strict.
Precisely. It can be too brittle. To address this, there's containment exact match, which is a bit more flexible. It checks if the VLM's answer is contained within the correct answer after removing things like articles and extra spaces.
Okay, a bit better.
There are also token overlapping scores like F1, RU, YE, and BLEU, which measure the similarity between the predicted answer and the correct answer based on the overlap of words or parts of words. However, the survey notes that these can be less effective for more complex, generative models that produce longer answers.
So as VLMs become better at generating longer and more nuanced answers, these simple matching metrics might not be sufficient to capture the quality.
Exactly. That's why some benchmarks, like MMVet, are starting to use LLMs themselves to evaluate the generated responses, especially for longer answers that require understanding the meaning, the semantics.
Using AI to grade AI. Interesting.
Yeah. These LLM evaluations tend to align well with human judgment, but can also have some variability depending on updates to the underlying LLMs or changes in how they are prompted. It's still an area of research.
Makes sense.
And as Figure 2b showed, using a multiple choice format is very common because it's just easy to evaluate. You just look at the percentage of correct answers.
Sure. A, B, C, or D.
Right. However, the survey notes a potential issue. LLMs can sometimes guess the right answer in multiple choice questions, even without properly using the visual information.
That's a bit concerning. It's like they might be getting the right answer for the wrong reasons, not actually engaging with the visual input.
Yeah.
The survey also mentions image-text similarity scores for benchmarks that evaluate image generation, right?
Yes. For tasks like generating images from text, metrics like slip score and RJ are used. They assess how well the generated image matches the given text description, looking at both semantic similarity and the similarity of the words used. Overall, though, the survey makes an important point.
What's that?
That current benchmarks often prioritize having a large and diverse collection of test data quantity over really fine-grained measures of evaluation quality. This might be limiting our ability to truly understand the deeper capabilities and limitations of these models.
That's a really insightful point. It's like we're focusing on the quantity of tests rather than the depth of understanding they provide. Okay, so we have a good understanding now of how VLMs work and how we try to measure their performance. Now, what can they actually do in the real world? The survey has an extensive section on applications for us to explore.
Absolutely. The range of applications is truly remarkable, and it's growing fast. The survey starts with embodied VLM agents. What are the main areas where these are being applied?
It seems like there are virtual applications like personal device assistants that can understand what's on your screen and help you navigate apps or websites, or tools for interpreting visual charts and even generating diagrams for individuals with visual impairments. The survey mentions examples like Screen AI for understanding user interfaces, smartphone assistants that can perform actions on your phone based on visual input and language commands.
Like telling your phone to order something you're looking at.
Exactly. And ChartLemma is specifically designed for understanding charts and graphs.
What's particularly interesting here is the potential for these virtual agents to significantly improve accessibility and the user experience, making technology easier to use for everyone.
Definitely.
However, the survey also highlights a current limitation. These virtual embodied agents often rely more heavily on language-based reasoning, with vision playing a supporting role. This can sometimes lead to insufficient visual understanding for effective decision-making.
So the AI might be good at understanding the words asking it to perform a task on a screen, but might not always have a deep visual understanding of the screen itself. It might miss some context. That makes sense. The survey also mentions physical applications of embodied VLMs, such as surgical planning and simulation.
Yes, this is a growing field where VLMs can process medical images, like CT scans or MRIs, and provide valuable insights for surgical procedures, potentially reducing risks and improving outcomes by helping surgeons plan.
Wow, that's high stakes.
Very. Then the survey moves on to generative visual media applications. It sounds like a more creative area.
This is where the meme generation comes in. Platforms like supermeme.ai utilize VLMs to create customized memes in a wide variety of languages based on text prompts.
Generating humor, that's tricky for AI.
It is, and apparently they're also being used for cinematic and visual effects like MovieGen, which can generate video effects from static images, sort of animating pictures based on descriptions.
It's quite amazing how these models can understand and generate creative visual content. Now, let's discuss robotics and embodied AI, which the survey emphasizes as a very active area of research. This feels like a major frontier.
Yeah, this is where VLMs bridge the gap between the AI and the digital realm and actual physical robots, right? Getting AI into the real world. The survey breaks this down into manipulation, navigation, and human-robot interaction. Let's start with manipulation.
Okay. In manipulation, the focus is on enhancing robots' abilities to handle new objects and plan complex actions using their understanding of language and vision. The survey mentions models like Vima, Instruct2Act, and the RT series from Google,
Right.
which are all aimed at enabling robots to perform tasks based on visual input and natural language instructions. Pick up the red block.
Got it. But what's the challenge there?
A current challenge is achieving a high level of generalization. Given the vast diversity of robot designs, different hands, different sensors, and the sheer variety of real-world objects, getting a robot to reliably handle things it hasn't seen before is tough.
So a robot trained to pick up a specific type of bottle might struggle with a bottle of a different shape or size, or maybe one that's slippery. Makes sense. What about navigation?
Here, the goal is to enable robots to navigate in real-world environments based on language commands, go to the kitchen, or visual cues that have semantic meaning, find the door with the exit sign. The survey discusses systems like Ziason, LMNav, and VLFM.
Okay.
These allow robots to understand natural language goals and navigate complex spaces to reach them. Many of these approaches still utilize task and motion planning, or
TAMPI.
task and motion planning. It basically breaks down a high-level task into smaller executable steps.
That makes sense. Breaking down a complex request like go to the living room and bring me the newspaper into smaller steps like recognize the living room, navigate towards it, identify the newspaper, pick it up, etc. And then there's human-robot interaction, or HRI.
Right. This area focuses on making robots better at understanding human intentions and adapting their behavior accordingly, making them better collaborators.
Okay.
The survey highlights models like MUTEX, LAMI, and VLM Social Nav, which are improving robots' abilities to collaborate with humans, learn from demonstrations, and navigate social situations like moving through a crowd in a more intuitive and compliant way.
It sounds like VLMs are making robots much more user-friendly and adaptable partners, less like programmed machines and more like helpful assistants. The survey also touches on autonomous driving. That's another significant area.
Absolutely, a huge one. In autonomous driving, VLMs are being used for things like more accurate object recognition, identifying pedestrians, cyclists, other cars in complex conditions, as seen in VLPD. Also, navigation and path planning with MotionLM, decision-making as in DLU.
Decision-making, like deciding when to change lanes.
Exactly. And even end-to-end models like VLP and Drive GPT-4 that aim to directly control the vehicle's steering, acceleration, braking based on the combined visual and sometimes language input, like understanding traffic signs.
So the AI in self-driving cars isn't just identifying cars and lane markings. It's starting to understand the broader context, maybe predicting what another driver might do and make more human-like driving decisions.
That's the direction the research is definitely heading. However, the survey also points out some important limitations in robotics in general. These apply to driving too.
Okay, what are they?
One is the trade-off between the ability to generalize to new situations and the flexibility to perform a wide range of tasks. Tampian-based approaches can be modular and interpretable, but might struggle with unexpected events not in their plan. End-to-end methods might learn complex behaviors, but could be limited by the specific data they were trained on and harder to understand.
Right, the black box problem.
Exactly. There's also the crucial challenge of balancing intelligence with safety, ensuring that robots powered by VLMs behave predictably and safely, especially in safety-critical applications like driving or surgery. You can't have them hallucinating there.
Absolutely not.
And finally, the challenge of embodiment itself, bringing these cutting-edge, often massive VLM capabilities onto actual robots, which often have limited onboard computational power and energy. This often leads to using older or less powerful models or relying on cloud connections, which introduces latency.
Those are really critical considerations. You can't have a robot making unpredictable decisions or a self-driving car misinterpreting a situation with serious consequences. The survey then moves on to human-centered AI. This sounds like using VLMs to directly benefit individuals in various ways.
Exactly. This is about leveraging VLM capabilities for direct human good. This includes web agents, like we mentioned, that can assist people with interacting with web pages, filling forms, finding information, maybe even booking appointments. Models like Cod Agent, Web Voyager, Screen Agent are examples. Accessibility tools are another major area, helping individuals with disabilities understand visual content. Think of generating rich descriptions of images on websites for screen reader users, or describing virtual reality scenes. X-World is mentioned here.
That's fantastic. Real potential to improve lives.
Definitely. Applications in healthcare are also highlighted, such as medical image analysis, detecting anomalies in X-rays or scans aiding diagnosis, and generating explanations of medical findings. Vision Unite, MedClip, MedFlamingo are some models in this space.
But the survey mentions the need for very high accuracy here, right?
Extremely high. The stakes are incredibly high in healthcare, so accuracy, reliability, and validation are paramount. And finally, the survey touches on leveraging VLMs for social good in areas like education, helping with mathematical reasoning, or even teacher training simulations.
Interesting.
Agriculture, like diagnosing crop diseases from images or optimizing farmland use, fundamental science research, climate change modeling or monitoring, bias mitigation in AI itself, and even urban planning.
It's remarkable to see how broadly these models can be applied, from helping someone navigate a website more easily to potentially aiding in the diagnosis of serious medical conditions and even tackling big global challenges.
They certainly hold a great deal of potential. However, as we discussed earlier, and as the survey thoroughly outlines, there are still significant challenges facing VLMs that need careful attention.
Right. It's not all perfect yet. The survey focuses on areas like hallucination, safety, fairness, alignment, efficiency, and data. These seem crucial.
They are. These are the roadblocks the community is actively working on.
Let's start with hallucination again. We touched on it, but what progress is being made? The survey mentioned various data sets and metrics researchers are using to understand this better.
Yes, there's been a lot of work in this area. Initial efforts like CHAIR and POPE relied on human evaluation to identify cases where the VLM referred to objects that weren't actually present in the image factual errors. More recent research has focused on understanding why hallucinations happen, how factors like the amount of training data, its quality, and the level of detail in the annotations affect it. Benchmarks like HallusionBench, GIE, HaliVol, and AMBER aim to provide more comprehensive evaluations, sometimes even automatically generating diverse examples of hallucinations to test robustness.
So it's not just about whether an object is there or not, but also about the accuracy of the details, colors, positions, counts, and the overall consistency with the visual information, getting the nuance right.
Exactly. It's a finer-grained understanding of faithfulness. Now, what about safety? That's obviously a very important aspect, especially with generative capabilities.
Yeah, how do you stop them from being misused?
Given the wide range of potential uses for VLMs, ensuring their safe and ethical deployment is crucial. The survey discusses the issue of jailbreaking, where people use clever prompts to try to trick the models into generating harmful, biased, or inappropriate content, bypassing safety filters.
Right, adversarial attacks, basically.
Precisely. Benchmarks like SafeBench, MMSafetyBench, and JailbreakV have been developed to specifically assess these vulnerabilities. Researchers are also investigating potential attacks, like ADs and MGJP, that could exploit weaknesses in the models, often by embedding malicious instructions in images.
It sounds like there's an ongoing arms race almost, between building safeguards and finding ways around them. What other challenges does the survey highlight?
Fairness.
Yes, fairness is a major concern. VLMs, like other large models, can inherit and even amplify biases present in their training data. This can lead to disparate performance for different demographic groups.
So a model might be better at recognizing faces with certain skin tones than others, for example.
Exactly. Or exhibiting gender stereotypes or performing poorly on images from certain cultural contexts. Benchmarks like MMBias, FMBench, Harvard Fair VL, and Cultural VQA are being developed to measure these biases across dimensions like gender, skin tone, age, and culture. Addressing this is critical for equitable deployment.
Absolutely. What about multimodality alignment? This is another key technical challenge. It refers to inconsistencies or a lack of proper connection between the visual and textual information within the model. If the vision part and the language part aren't well aligned, it can contribute to hallucinations or misunderstandings.
So the two senses aren't communicating properly.
Kind of. Researchers are exploring ways to improve this through mechanisms that allow the model to perform self-reflection or self-critique, double-checking its reasoning against the visual input. Also, designing better projector modules or attention mechanisms to connect the modalities more effectively, as seen in models like SIMA, SAIL, and 1LM.
Okay. And efficiency. These models sound huge and expensive.
They are. Efficient training and fine-tuning is a major area of focus. Training these large VLMs from scratch requires massive computational resources and energy. So there's a lot of research on understanding how the initial pre-training phase affects the final performance. Maybe shorter pre-training is sufficient sometimes. And developing more efficient fine-tuning techniques is key. Techniques like low-rank adaptation, or LoRa, which only updates a small subset of the model's parameters, or using reinforcement learning with human or AI feedback, RLHF or RLAIF, to align the model more effectively with desired behaviors without full retraining.
Makes sense finding ways to adapt them without starting over. And finally, data scarcity.
Yes, the scarcity of high-quality datasets remains a persistent challenge. The performance of VLMs heavily depends on the data they are trained on, and there's a constant need for larger, more diverse, and better annotated datasets, especially for specialized domains like medicine or robotics.
So how do we get more good data?
Potential solutions being explored include better self-supervised learning techniques that can learn from unlabeled data, generating high-quality synthetic data using other powerful AI models, though with careful validation, and gathering data from interactions in simulated environments or through interaction with world models.
It sounds like while we've made incredible strides, there are still some fundamental challenges, technical, ethical, practical, that need to be addressed before VLMs can be truly reliable and broadly beneficial across all these potential applications.
Absolutely. The rapid advancements we've witnessed, particularly since 2022 or so, are truly remarkable. The potential applications are transformative, impacting everything from our personal devices to sophisticated robotic systems and even critical fields like healthcare. However, these challenges, hallucination, safety, fairness, alignment, efficiency, data, require continued focused research and very careful consideration as we deploy them.
It's an exciting but complex picture. So wrapping up, considering how VLMs are learning to see and understand our world in these increasingly sophisticated ways, what kind of new interactions do you envision between humans and AI in the near future, maybe 5, 10 years out?
Oh, that's a great question. I think we'll see much more seamless integration. Imagine AI assistants that don't just respond to your voice, but can actually see what you're doing, what you're pointing at, and offer help in context. Maybe helping you assemble furniture by watching you, or diagnosing a plant problem from a video you show it. Or perhaps truly collaborative robots in workplaces and homes.
That sounds incredibly intuitive, but it also raises questions, doesn't it? What practical or maybe ethical considerations should we be really thinking about now as these models become even more integrated into our daily lives?
That's the crucial part. Privacy is huge.
Yeah.
These models are seeing our world. Data security, the potential for misuse, like generating deepfakes or enabling autonomous surveillance. Job displacement is another complex issue, and assuring fairness and preventing bias from becoming even more entrenched in automated systems. We need robust regulations, ethical guidelines, and ongoing public discourse alongside the technical development.
Definitely a lot to think about beyond just the technology itself.
Well, this has been incredibly insightful. Thanks for diving deep into this fascinating survey with me.
My pleasure. It's
Yeah.
a rapidly evolving field. And yeah, staying informed is essential. There's always something new just around the corner.